informational and as well as as uh, entertaining as well. All right, so what I'm going to do now, I'm going to start recording. So I believe I am recording right now. Okay. All right. So this is a good stuff here. So tuning of a PID, obviously tuning a PID controller is just adjusting the tuning parameters. So we have the proportional, we have the integral or reset. So there's two couple of different terms there, and the derivative or rate. So obviously, as you know, I teach loop tuning courses, and but as I ask all the time, what is the most popular tuning method out there? And it is a tune by feel. So people over the years have developed, well, I think for this, I'm going to put a little bit of this, a little bit of that. And eventually, okay, all right, that's good enough. And let's move on to the next control loop. And in my courses, I teach lambda tuning. So I just want to make sure that there are scientific ways of actually tuning a control loop, a systematic way of tuning a control loop. And once again, how you tune and control your control loop tuning parameters must match the process. And I think we talked about that in my first episode 1, where if we build ourselves a very slow process, we design a very poorly designed a process that reacts slowly, that will obviously impact upon how we're going to be able to tune it. So let's take a look at the PID. So this is the ISA or ideal form of the PID controller. Now, there are other ways of plumbing up a PID controller, but we'll deal with this one. So how does this work? So you got your process value. So this is your measurement coming back. So maybe I can get my laser pointer going here. Got my laser pointer. So you got you got your process value. So this is the value coming back from your measurement, be it a pressure measurement, level measurement, flow measurement. And set point, this is where we want to be. So the first thing that happens is that we will subtract where we are and where we want to be. And the difference between the two is called the controller error. And the PID algorithm will react based on the controller error. So let me go back. So after that, the proportional part goes straight through. You got the integral action or reset and derivative or rate go this way here. And yes, there is an actual transfer function, Laplace transfer function there, and that's the actual Laplace transfer function for a PID controller right now. So don't worry, this will not be on your test at the end of this session. But what I want you to show is that there is application here between actual theory and practice, and some of the tuning formulas, the tuning methods are based on using these transfer functions right now. So, okay. So what I'm going to do, we're going to break it down individually for proportional, integral, and derivative. So once again here, let's take a look at this. So we got our set point here and a PV. This is where we want to be. This is where we are. Once again, we're going to subtract one from the other. Now the proportional part will take the error, multiply it by the proportional, and that makes its way towards the controller output. So let's take a look at this in a different way. So once again, as I said, proportional moves the output proportional to the error. Now imagine, and I'll do a demonstration on this in a minute, but imagine if I have a PID controller, but I'm actually have 12 milliamps going into my analog input, which is 50% of span. And I'm going to measure the output of the PID. There's no actual process here. So I'm isolating the PID controller. So here we are. So the PV and set point are both at 50%, error is 0. And there suddenly I make a set point change from 50 to 60%. So now I have an error of 10%. So proportional will move the output proportional to the error. Now let's put some numbers on here. Let's say my gain is 0.5. So what happens is that if my output of my controller starts at 35%, when I change my set point, I got an error of 10%. 10% times 0.5 is 5%. My output will move to 40%. It will actually change of 5%. Now, some of you may know proportional band instead of proportional gain, and that is how you actually convert from proportional band to proportional gain, is 100 divided by the gain. So a gain of 1 is a proportional band of 100%. If I increase the gain to 2, corresponds to a decrease in proportional band to 50%. So let's just do this demonstration here. So I will show you. So this is actually here the lab that I use for my tuning courses. So I'm going to go down right to here. And off we go. So what I want to show you, this is the actual tuning parameters right here. I got a gain of 0.5. I got an integral action of 10,000. The reason why I have 10,000 right here right now, and you'll see later on, is that the higher the number for integral for this integral or reset value, the less you have. It's inversely related. And I have rate or derivative, I have it set to 0. So here I can actually change the actual input. I have the ramp if I want to turn it on. I can add some noise. And this is my output of my controller. There is no process. There is no feedback between the output back to the input. So let me actually demonstrate this. So, okay, so what are we seeing here? So this is just a plain old PID controller. The blue line, the blue side here, is the output of the controller. So it is this value here. The yellow is the actual measurement, the yellow bar, and the white is the set point of the controller. So I'm going to put this controller in automatic. So now set point is 50, PV is 50, error is equal to 0. There is no control action. So I'm going to put this over here. Now remember, the gain is 0.5. So what I'm going to do now, I'm going to change the set point from 50 to 60%. That means I'm going to have a 10% error. 10% times 0.5, my output should change by 5%. So let's give that a shot. And there, so you can see here, as I click down over here, I can see the value. It may be hard for you to see, it's at 60%, and I made my set point change, and my output went to 65%, just as we predicted. So now what I'm going to do, I'm going to put it back to 50, and my output's going to come back to where it came from. Now I'm going to change this value here from 0.5 to 1.0. So now I get a gain of 1. I'm going to make the same set point change. Now I got more gain. I'm going to get more action, more changes on my output. I'm going to go back to 60. And now you can see I have more proportional action because I increased my proportional gain. So here it went from 60% to 70%. So I'm going to put this back to 50%. Here we go. Okay, so that was for proportional action. Let's talk about integral action or reset. So once again, the error gets pre-multiplied by the gain. So it's very important here. For this structure here, the error gets pre-multiplied before it passes through the integral action, and then it makes its way to the controller output. So let's take a look at it. What is integral action? It is an integral. It integrates the error. So just like a totalizer. So if some of you may know what a totalizer is, you got a flow going by, you want to totalize that flow because you want to know how much volume has gone through or how much mass has passed through that meter. It's the same idea here. So once again, let's put some numbers on there. So PV is equal to set point here. I make my set point change from 50 to 60%. I get an error of 10%. So let's put some more numbers. Let's say my integral action value is at 30 seconds per repeat. 30 seconds per repeat. So I make my change here, and here obviously is my proportional kick. I can't get around that because obviously proportional will come into play at the same time. But then after that, integral says, well, you're still not at set point. I'm going to add more to the output. You're still not there. I'm going to add more. 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 The key here is that it will actually eventually repeat the proportional action after the integral time, hence the term seconds per repeat. So after 30 seconds, it will have reached 45%. And as the air is still at 10%, after another 30 seconds, it will be at 50%, and so on and so on. Now, if I were to reduce this value from 30 seconds to 15 seconds per repeat, that means it will actually repeat the proportional part in a shorter amount of time. Does that mean I have more or less integral action? And the answer is you would have more, because obviously you have a steeper slope. And my little brain, what I actually think is actually that 15 seconds is faster than 30 seconds. Typically, the units are seconds per repeat, minutes per repeat. However, if you do go do some tuning, you need to understand the structure of your PID block. Some of them can be in repeats per minute. Some of them can be in repeats per second as well. So it's critical to know not only the structure of your PID controller, but as well as the units that you're using. So we're going to go back and do another demo. Isn't that exciting? So you should see here we actually had our proportional actions going on here. So what I'm going to do now, I'm going to change this value from 10,000 seconds. I'm going to put it to 20 seconds. My gain is still 1. So now my output is at 60%. So what do I predict is going to happen? I'm going to make a 10% set point change. I'm going to go from 50 to 60%. I'm going to get my initial proportional kick of 10%. And then after that, after 20 seconds, the reset will have continued ramping and will eventually repeat the 10% proportional change in 20 seconds. So let's do that. So there's my set point change. So now you can see integral is actually winding up now. And after a while, so I'm going to put this in manual for now, so we don't wind up too far out. So this here is my proportional kick. So from there to there, went from 60 to 70%. And that happened at 11:19:30. I'm looking at the time scale at the bottom. So what I'm saying is that after 20 seconds, so at 11:19:50, if my math is gooder than my English, we should have reached 80%. And actually probably stopped it a little bit too short, but actually 11:19:50 is at 79.6. So you could see here that this part, the integral repeated the proportional part in the prescribed amount of time. So let's just change this a little bit here. So what I'm going to do is that I'm going to put the output back to 60% where I found it. I'm going to put this back to 50% where I found it. And now I'm going to make this 10 seconds. So now the integral will repeat the proportional part in 10 seconds. So I'm going to put this back in automatic. Bring my trend up. And now I'm going to change this to 60%. There's my proportional kick again. But now you can see it is ramping up faster than before. So I'm going to put it in manual again. So here I'm at 11:21:23. So that means I say that at 33 I should be at so it went to 70%. So at 24. So therefore 24 seconds plus 10 is 34 seconds. And it's right about I got 11:21:35. I'm at 80.2. So once again, it repeated the proportional part in 10 seconds. Okay, so that's sort of that is a demonstration for integral action. Now I'm sure you're all excited about the next one, derivative. I always ask people, what does D stand for? And they always say, oh, it stands for derivative. And I say, no, it doesn't. It stands for don't. It stands for doom. It stands for disaster. So how does derivative work? It's usually out of, we'll see that later on, but actually out of 100 loops, probably I did a survey of my Lakeside Tuning Index, and about 10% actually have significant derivative tuning in them. Not to say that 10% should, but 10% do. So we can take a look at that. Derivative or rate will move the output proportional to the rate of change of the air. I don't care if the air is there or not, if the air is changing. So you can see here, I got set points at 50%, PVs at 50%. Then I make a set point change from 50 to 60%. Very, very fast change. And what's going to happen is that now I'm going to have a massive derivative spike. However, afterwards, though the air is still present, not changing, the air is still at 10%, but not changing. Therefore, there will be no more derivative action. So because of this will not be a very practical aspect. For every time the operator would make a set point change, it would actually cause a derivative spike, not very good for the most processes. So most of the time, derivative will be done on the PV and not the air. Derivative has units of seconds or minutes. So let's take a look at it here from a block point of view. So like I said, derivative is typically done off the PV. From a low disturbance point of view, not a set point change, but from a low disturbance point of view, there's no difference if we do the derivative off the PV or off the air. And in this way, at least we avoid derivative spikes every time the operator would change the set point. One last thing, derivative is very sensitive to process noise, to measurement noise. So if you think of measurement noise as actually kind of fast variability, derivative doesn't know if it's actual disturbance or noise, and it will react based on the change of response, the speed of change of the air itself, which is caused by the noise on the PV. So once again, we're going to do another demonstration here. I'm sure people are very excited about this. Okay, so now I'm going to change this back to 10,000. I don't want any derivative, any integral action. And I'm going to put this to 10 seconds. So my PV, I got to change my set point back to 50%. Put my output back to 60%. I'm going to put this in automatic. There we go. Okay. So first thing I want to show you is that here, this algorithm that I chose does derivative off the PV. Okay, so therefore, if I got to change my set point here from 50 to 60%, the only thing I get is proportional action, because if I'm doing derivative off the PV hasn't changed. There is no derivative action. First thing I want to show you. So put that back. So how do I get to examine the derivative action? I'm going to change the actual input into the PID. So I got to change this yellow value here. And this is where you're going to see the derivative spike. So you change that from 50. So pay attention to the 60% up here as I change it. So there you can see that it actually reacted. So obviously here it reacted the opposite because I increased the PV. So therefore the controller reacted the opposite. And you can see here that is a derivative spike I was actually talking about. The PV, the output then remains here, which is actually at 50%, because that is the proportional. What remaining from here to here is the proportional action. So I got to put this back to 50%. And once again, you'll see the derivative spike. You can see here, actually, it went all the way up to 100%. So something we need to avoid. And that's why we do derivative off the PV and not the output, not the error of the signal. So now what I'm going to do, I'm going to introduce a ramp. So now when I make a change here, it's going to be passed through a rate limiter. So now the error is going to change progressively, and you'll see the error, you'll see derivative then acting on that growing error. But after, when ramping is done, you will have no more derivative action because the error is steady. Let's take a look at that. So now you can see there's the error, the PV going up. What you see there, you actually have your proportional kick, and then you got your derivative action. And once the error is, when the PV has stopped changing, you can see here that what's remaining, again, from here to here is the proportional action. So now what I'm going to do before I make a change back, I'm going to increase this to 20 seconds. And now I'll be having more derivative action. The higher the number for rate or derivative, the more you get. So I'm going to put that back to 50%. And let's take a look at it here. You can see here definitely a lot more integral, the derivative action. And then as the PV stops from moving, after the ramp is done, we come back to where the proportional part is done its work. So last thing I want to show you is the fact that the PID, that the derivative is sensitive to noise. So what I'm going to do here is that I'm in automatic, and now I'm going to introduce some noise here. So this is just random noise, a value, the peak-to-peak value. I'll select 2% for now. And see what effect it has on it. And you can see now just random variations, really has nothing to do with the measurement, but now the derivative action is obviously reacting very, very much to that. Now, if you imagine that you're actually connected to a process, you would probably induce variability because of your tuning. So here, if I were to reduce that to 3 seconds, because I like the number 3. So now I should have less changes, responses to the noise, because I have less derivative action, as you can tell right there. Okay. So that concludes that demonstration. So we just talked about the P and the I and the D and what do they do. I was able to isolate the PID algorithm, so therefore we can make changes and see how the PID controller reacted to those changes, be it set point or PV. Let's talk a bit more about the P and the I and the D and how they are actually being used in the industry. Now I've developed what I call the Lakeside Tuning Index, and I've been examining and analyzed the tuning parameters, amongst other things, the tuning parameters of almost 5,000 PID blocks. One of the things I noticed is that only 1 in 5 are well tuned. What does that mean? It means that they fall within good practice for that type of loop. Be it as a flow loop, I know what the tuning should be. If it's a level loop, I know what the tuning should be, and so forth. Believe it or not, 1 in 6 have default tuning. That means they've never been tuned. 1 in 6, 16.7%. Incredible. And 1 in 3 actually have what I call suspect tuning. Can't call it bad tuning. I have to be politically correct and sensitive, so I call it suspect tuning. And that means that the tuning of that particular loop does not match what would be for that particular type. So as for instance, for a flow controller, it may have a controller gain of 1.2 and an integral of 35 seconds per repeat, well out of the ballpark for what should be the typical tuning for that particular type of loop. And so we talk also about optimization programs to be able to reduce energy costs and all the good stuff. I'm sure most of you know all about that. And so through that, the basis of any kind of optimization path starts with the Lakeside Tuning Index. How do I generate it? From the DCS database, I can take a database export, and I examine each, and I actually assess if the tuning for each loop is good, questionable, or suspect. Now I also look at PV filtering as well. So, and that's actually kind of falls into my next session in April. We're going to talk about PV filtering, PV dampening. And if I find that a particular control loop has excessive amount of PV dampening, it might be an indication that there is a measurement problem. That's how we kind of sweep it under the rug and try to hide the problem. Other things, PID algorithms can also have some what I call nonlinear free features like dead bands and things like that. Could be an indication of a valve-related issue. Now, I generate a dashboard of your results, and I compare it to the industry average. So you can see here, this one, there's a lot of what I call duplicate tuning. That means there are 2, 3 or more control loops that have exactly the same tuning parameters. So probably some sort of copy and paste kind of issue there. And that means that one may have good tuning, but the next one has exactly the same. Probably means that it doesn't mean that tuning is bad. It means that it's never been properly bumped, analyzed, and tuned. Here's another one here. This is one of our customers. Almost 50% of the control loops, all the PID loops, had default tuning. That means they were never tuned. And actually, I've been there a few times now to go and actually address and tune those control loops. And this one here, actually, what stands out is for this particular customer, it's the PV filtering is greater than 4.9 seconds. This one here, we suspect that there may be some significant measurement problems throughout their plant. And we're also in talks with them going through each individual loop to make sure that, if there is an excessive amount of dampening, why is it? Most of the time, remember we talked about specified, install, and maintain. It may not have been properly specified, installed, or possibly not maintained well. And you can do that. You're more than welcome to send me your DCS database. It's a free service, and I will generate a dashboard for you. So we're almost there. My next session is April 14th. I certainly hope to see you there. It's about is it noise or is it music? And it's the truth about signal damping. So we talked about PID, but now why do we use dampening? What is noise? And we explore that. And what are the consequences of putting in too much dampening on our PVs? And that is April 14th. It's on our website. You probably might get a notification within a week or two. And I certainly hope to see you there. So we're here at the question period. And as I said, I have a 10-second time delay. So I will wait to see if you have any Any questions? There is one question, and person asks if you can get the slides, and the answer is you will actually be getting a video link. So the video link will kind of replace the slides. Don't be shy. I'm still waiting. Like I said, it takes a while for the signals to get to my space station. This question is session 1 available. I will ask, see if that video is available, and I will. This is all being recorded, so I will probably be able to send you that link for that video. Another question, so how the tuning shall be done. So when you do loop tuning, the procedure is obviously know thy process. So the first thing I need to do is I put the control loop in manual, and then I make step changes in manual. From that, I will actually able to identify what the process parameters, I identify the process sensitivity, process gain, not the controller gain. I will determine the time constant. I will measure the time delay of the process. And from there, I will use those numbers in my tuning calculations using the lambda tuning method. And so that's how you use the information from your process in your tuning. That's how your process matches your tuning, or your tuning matches your process. That is actually how I go ahead and tune it. Is there any process that will use derivative? Excellent question. Yes. The best candidate is temperature control. Temperature controllers are typically clean signals. They're not noisy at all. And what derivative does is that it allows you to overcome some of the process inertia, especially if you have a lot of heat transfer. If I were to actually, give me a second here, if I'm able to draw, if you look at your screen. So if I were to do a step change, a temperature controller will react like this very slowly. So if I use derivative, if I make a set point change here, what my output is going to do with derivative, or if it will actually kickstart the process, the output. So we'll try to overcome some of the inertia of the process. And as it's approaching the PV, I'll say, oh, I was just kidding. I'll bring it back down here. So derivative is good at overcoming process inertia. Excellent question. You guys are great. Thank you. I'm just trying to see any process. Then starting gain, then I, then D if required. So someone is asking, how do you do this? Again, it's there's no kind of quick and dirty way of tuning a control loop. I mean, I do have over 30 years experience. I have a good idea where values should be. But the idea, again, is to methodically do your bump test, calculate your process parameters, and then from there, that will impact on how you tune your control loop. Says, so another person, gain and reset ranges for gas pressures controlled, derivative usually 0, right? That's another excellent question. Gas pressures are very different from liquid pressures because gas pressures are what we call integrating process. So once again, I'll go back to my screen here. And there are two types of processes out there. There are self-regulating processes like a flow, where I increase the output, the flow will go up and then stay there and hover. Integrating processes are like tank levels and gas pressures, where they will actually either ramp down or ramp up. And the reason for this, especially for a gas pressure, is called, if we all remember, PV is equal to nRT. So if you think of a steam header, so therefore the volume of the steam header is constant, R is constant, let's say T is constant, N is a number of molecules, will have a direct impact on the pressure. If I'm putting more steam molecules in my steam header than I'm consuming, I'm accumulating steam molecules in my header, that number goes up, and then the pressure will go up as well. And the obviously opposite is true as well. So, and yes, typically derivative is 0 for gas pressures. So another question, how do you decide on tuning values for the PID? Does each tune value affect the other? For a ISA ideal form, for the classical form or series form, the answer is yes, one can affect the other, especially the gain, because the gain pre-multiplies the error before it actually goes to the rate and the integral. So definitely one, so adjusting the gain will affect the other two as well, definitely. Cascade control loops. Which loop should be tuned first, inner or outer? That's another excellent question. So a cascade loop is a type of loop where the output of one PID controller becomes a set point of another PID controller. An excellent, good example for tank level. The level controller looks at the level. My level is low. It will increase the output and will actually increase the set point of a flow controller, who will then increase the flow, which will bring the level back up. You always need to tune from the inside out. So the inner loop needs to be tuned first. And the reason for that is the fact that when you do your bump test on your outer loop, you must have the inner loop in cascade mode or remote set point or external set point, whatever you call it. It has to be, because how you tune that inner loop becomes part of the process as far as the outer loop is concerned. Excellent questions. I love these. You guys are great. You guys are great. Another question. Any recommendation for tuning pH control loop when you're running at the steepest point of the titration curve to avoid overshoot? Oh my God, you guys are great. This is another excellent question. Recommendation. So what this person is referring to is the fact that pH, if you're neutralizing a strong acid with a strong base or a strong base with a strong acid, is a highly nonlinear process. That means that if I make step changes all the way across, the process sensitivity will be very different at the bottom end or the top end of pH 3, 4, and 5, or 8, 9, and 10, that it will be at 7. At 7 will be very, very sensitive. And so obviously your process is changing depending on where you're operating. So what I recommend is something called gain scheduling or adaptive tuning. Either terms are interchangeable, where depending on where you are, you adapt, you change your tuning, and that will minimize overshoot. So therefore, as you stray away from the highly sensitive around pH 7 point, you will increase your controller gain because your process gain is decreasing. And as you're approaching your pH of 7, you will actually decrease your controller gain to maintain the same overall control loop stability. That's an excellent question. Thank you very much. There's another question here. What about highly viscous liquids, such as plastics? Should I add derivative as we do temperature, as the pressure or flow sometimes change with a delay? That's a difficult question to ask. We would have to see how the process responds. Viscous liquids, if I were to imagine, it probably is slow moving. It probably responds more like this over here on my screen than it would like this. And so perhaps derivative may be a candidate for that as well. Another question. If your PV oscillates your set point and almost never settles, how best can you tune this? So what I presume there, two things. If your PV oscillates your set point in manual mode, then that would mean that there's something else disturbing your process, and therefore we need to find that source of disturbance before we can tune this PID controller in itself. If your PV oscillates your set point in automatic mode, that could be a few things. One, it could be the maybe your gain is probably too high if it's a tuning issue. But remember, tuning is the last thing you do. So what I would think there is there could be related to possibly a control valve related issue. So if your control valve, if your PV is oscillating, and again, taking a look at my screen here, if my PV is responding like this, like shark fin pattern around my set point, and my output is operating like a triangular pattern, that's a sign that my valve is sticking or has some sort of deadband or hysteresis or sticking, probably by this much. And it's one of the first things I look at when I actually go in a control room. I look at all the trends. If I start seeing triangular patterns, that's an indication that could be a valve-related issue. So therefore, those are the two scenarios that I can imagine. That's excellent. Are there any other questions that I haven't answered here? Let me take a look. So how is it to be done? Is there... So there's another question. Okay, most process control loops are first order closed loops. Are there any example of second order closed loop, for example, in the oil and gas industry? So what this person is asking about is actually, again, if I were to point out that this here would be a first order, or we would approximate it to a first order plus dead time type of control loop. If you have a second order, multiple order, it would behave more like this one right here. Other types, we usually typically will model temperatures as second order processes, and that's why, because we approximate 2 time constant as opposed to 1 time constant, we approximate that, and that's why we need the D part to try to handle. They will handle 1 time constant, and the integral will actually handle the other time constant in the oil and gas industry. So again, there's probably temperature control loops definitely in the oil and gas industry that could probably utilize some derivatives. I always think people have a fascination with derivative. So I have another question here. So got following up on the pH control, can you briefly touch on how the adaptive gains are determined? I assume that this can be complex, so looking for a high level description. Okay, let me try and do this. This will be, again, just as again here as shameless commercial plug there. I do teach adaptive tuning in my second loop tuning course. If you remember at the beginning there, I talked about process control techniques 1 and 2. I do actually teach that in my second course, and that you need to take the first course to take the second course. And so, like I said, the one March 30th and 31st is full. The second session will be in the end of April. You can sign up for Process Control Techniques 1, and then you can sign up for Process Control Techniques 2. Commercial break over. All right, let's talk about this. So pH control. So as I step my caustic valve, I'll use caustic valve over across the range, my pH will go up a bit more, go up, really up, and then not so much, and not so much there. So you can see it's a very nonlinear process, and right around here is most sensitive. So my process gain, again, I want to emphasize process gain, process sensitivity, not controller gain. The process gain, if I were to draw it out, this is 7 here. and this is my process gain, I call it KP, process sensitivity, will go up around 7 and then come back down. So we need to understand how our process is changing over the operating range. And we need to understand that before we can actually even implement a actual adaptive gain. And so what I would do then is that, knowing where we are operating on our pH, I will then adjust the gain based on where we are. And typically, again, pH 7 here, my gain would do the inverse of this and come back up like that. So the inverse. So therefore, as my process becomes very sensitive here, I will actually then decrease my gain there, and that will maintain overall stability over the wide operating range. Excellent question. Any other questions? I'll give it another 20 seconds. Once again, if you have a question, you think of a question afterwards, you are more than welcome to reach out to me, and I will certainly answer your question then. Okay. It appears that we have no more questions. As I mentioned, my next is April 14th. So certainly hope to see you there. Oh, I got one more questions. Oh, they're coming in again. Awesome. All right. So before I do that, okay. Any references, books that could refer to tuning? Yes, you can. There are many books out there. Probably some of the better ones are anything by 𝗦𝗓𝗦𝗬𝗓. So just do research on that, and you can see he's got some excellent references there. Again, or you can always attend one of my training seminars. I got an excellent book that comes with it as well. Another question: if your final control element valve is oversized and only controls well at higher flows, is adaptive control needed? Oh my God, that's another excellent question. So let's take a look at that. So someone is talking about if the valve is oversized, but can you tune it out for me? And so if you remember my episode 1, we talked about valve sizing, is that every time you do a step change, I mean, there's a lot that goes into sizing a control valve. The way I look at it is that a step change, and then that creates a change in my process. The ratio here of the change in my process to the ratio to the change in output should be between 0.5 to 2.0. That means a 1% change should cause a change in my process 0.5% of span to 2% of span. And so what happens sometimes is that I see my process gain, my sensitivity be 3, 4, or maybe 5. That means a 1% change causes a 5% change on my process. Very, very sensitive. And so this person is asking, can you use adaptive tuning based on this situation? I can't tell you, though, no, you cannot. You can use adaptive tuning in many places. The challenge here is when you oversize a control valve, and I'm going to get on my soapbox, is that small valve-related problems will translate into big problems in your PV. You cannot change the minimum resolution precision of a control valve. That is set. It is anywhere between 0.25 to 0.5% change. That's the minimum precision of a pneumatic, a very good control valve. It could be worse, but 0.25 to 0.5%. So putting in adaptive tuning may help it, but at the end of the day, you're still bound by that minimum valve precision. And I would really probably more look at the valve sizing. Now, if the valve is nonlinear, that is another situation here. So if you have, let's say, a butterfly valve, and butterfly valves have a quick opening flow characteristic. So this is my flow here. I apologize. And this is percent open. Open. Oh, you get the idea. So right around 50% here. Most of my flow change occurs before 50% and very little afterwards. If you have a butterfly control valve that's operating at 65, 70%, you're not controlling. You're barely modulating at all. And so I've actually implemented adaptive tuning. It's in the form of a characterizer. And this was done because it actually wasn't a butterfly valve. It was actually a globe valve on a boiler feed water. And the actual pump was wearing out, not the valve. The pump was giving out. And so what I had to do is I had to implement a characterizer on the output of the feed water flow controller like this in order to linearize the flow characteristic and allow the PID controller to be able to control better at the upper end. It's a Band-Aid solution, and it's done temporarily so that then they're actually buying a new feed water pump. But this one, it's a very large, it's 52-week delivery. So they won't be able to get it until when they do put the new pump there, we will actually have to take that characterizer out. Any other questions? You guys have been great. These are actually excellent questions. Okay. Like I said, if you have any more questions, feel free to drop me an email. Certainly appreciate. Thank you very much for attending. We had a good crowd here. Sad that I can't see you. Maybe here I'll turn on my camera here. This is me. So not a robot. I do exist. Thank you very much for your attendance, and I certainly hope to see you there at the end of in April 14th. Thank you very much.